Yes, we can see, we can hear you.
Okay. Good afternoon, everybody. It's my privilege to introduce Professor Abhishek Mukherjee. Dr. Mukherjee has been teaching as an assistant professor of mathematics at Kalna College, Kalna, West Bengal, for last 10 years. He is a guest faculty, Department of Mathematics, Kazi Nazrul University, since 2014. The University of Bardwan awarded him gold medal in pure mathematics in 2007 for his first-class first position. He has completed his PhD work at Department of Mathematics, Jadavpur University, under the joint supervision of Professor Dr. Sujit Kumar Sardar, Jadavpur University, Kolkata, and Professor Dr. Krishnendu Gangobardhay, ISAR, Mohali, Punjab. His research interest includes topology, geometry, complex analysis, hyperbolic geometry, and hyperbolic spaces. He organized a teachers' enrichment workshop conducted by National Center for Mathematics during December 27 to 31st in 2013 at Vivekananda Mahavidyalaya, Bardwan. He was the convener in RMS NCM Teachers Enrichment Workshop 2014, conducted by NCM on complex analysis and topology at Kalna College during 23rd to 27th December 2014. Currently, he is working in an Indo-Russian project in collaboration with ISAR. He will now deliver his lecture on an invitation to vector spaces. As requested to our previous speaker, I again request him to confine his lectures mainly within the syllabus for undergraduate students and then little more for postgraduate students. I hope the participants will be encouraged to learn more about the subject by his lecture. Thank you.
Thank you, Dr. Sheth. Now I request Dr. Mukherjee to deliver his lecture. Dr. Mukherjee, please start.
Okay, am I audible?
Yes.
Yes.
Yes, sir. Yes, sir. You are audible.
Yes, sir.
Okay, can you see my screen?
No, sir.
You need to pin my window actually.
Sir, please start sharing your screen. This is from administrator desk. Please start sharing your screen.
Okay. Okay.
It is visible.
Your screen is visible to
Okay, it is visible?
all the participants. Yes, sir. Your screen is visible to all participants.
Okay. So thanks to Bimalda and Joyanto Babu and my colleagues in HOOGHLY MOHSIN College for nicely introducing me to the audience. And since I will have a bit less time, so I don't know how much I can cover. So shall I start?
Yes.
Okay.
Okay, so my topic of my talk is an invitation to vector spaces. And as I wanted to give you some flavor of geometry and vector spaces, so I need to introduce first some aspects of geometrical observations and axioms and postulates, which will help us to develop the theory of vector spaces in axiomatic sense. Some noise is coming. I don't know why. May I request all the participants to please turn off your video and mic. Okay, fine. Yeah. So before going to introduce the theory of vector spaces, let me first depict an outline of the theory of the history of vector spaces, which deals with the motivation to study vector spaces, and also you will have a notion of geometry by using the axiomatization of vector spaces. And my interest is to give an inspirational lineup to visit the axiomatic theory of vector spaces, which is our modern linear algebra. Yeah. So now I am going to emphasize on the introductory part of vector spaces that has far-reaching impacts on many important wings of mathematics. And the axiomatic approach to study vector spaces was first introduced by the mathematician G. Peano in the year of 1888. So it has been introduced by G. Peano. So I know that it is well known to you that Peano's axiom for number theory, right? So he introduced the axiomatization of vector spaces firstly, but the theory did not actually took its nice form before 1920, which leads to a rapid development in 1930s, which comprises of a proper language that can be used in many branches, right? Okay. Now, in the meantime, if you go far before, that is in the year of 1637, so René Descartes, I think you know all this, his name. So he first brought the notion of Cartesian coordinates of Euclidean space. So what is Euclidean space? Euclidean space is the space where one can talk of classical Euclidean geometry, and which is basically in modern sense, it is R2 and R3. Just you are dwell in these spaces, that is R2 and R3. But in modern mathematics, one can generalize every aspects of lower dimensional spaces into any non-negative integer dimensional spaces, and which leaves your lower dimensional cases, that is R2 and R3, as particular spaces of Euclidean geometry. Now this geometry had been introduced by the, as you know, by the ancient Greek mathematician Euclid and Euclid of Alexandria, because there was another Euclid of Magog. So in those days, the Greek geometers were executing their experiments related to physical phenomena by extensive use of Euclidean geometry, where they proved all the properties of the underlying space as theorems by assuming some fundamental statements which are known as, which are familiar to all of you, maybe I think, so as Euclid's postulates. Okay, so let me, since I have a bit less time, so okay, so let me introduce the axioms of Euclid's. So basically there are 5 axioms, and which can be written like that. So okay, yeah. So the first one will be, so take any 2 points. So take any 2 points and then you can join a line, right? So there is a unique segment that you can have, right? So this is the first one. And let me first, okay, so we are in R3, yeah. So our set of points is R3. So we are living in this set, okay. So the second one will be that any straight line segment can be extended indefinitely in a straight line, right? So that is, if you have any segment, then you can extend it indefinitely. So these 2 axioms are actually, yeah, sorry. Yeah, okay, fine. And the third one is all right angles are same, right? All right angles are same, yeah. And the fourth one is also familiar to all of you, yeah. So the fourth one is that given any line segment, just regard one endpoint as a center, so you can draw a circle, yeah. And you will say that this line segment will be called radius of the circle, right? And the fifth one will be the most important thing that we know. So the fifth postulates. So this is like that if one straight line falls down on two straight lines, suppose this is L1, this is L2, and this is your L. And if the angles, this one and this one, that is, suppose it is theta and it is phi, denoted by theta and phi, then if their sum is less than 180 degree, then the conclusion is that the straight lines L1 and L2, if they produce indefinitely, will meet on that side of which the angles are less than two right angles. But which is more familiar to us, the statement, So the postulate that has been reformulated in the year of 1795, and it was by John Playfair, who offered another version of this postulate, and which is more familiar to all of us. That is, given any straight line, and if you consider a point outside that line, then you can draw exactly one line which is parallel to L. Now this is more, it produces some curiosity because this cannot be checked easily, whether they meet or not. So this is the case where you need to think of. Okay. So now, by introducing these axioms, I'm just going to have a look at an example which is very much classical, and it will give you a bit of notion how the theory develops, right? So for this reason, let us suppose that, so if this is 2 points, these are 2 points, so suppose it is P1 and this is P2, suppose these are 2 distinct points, so the line segment from P1 to P2 is the direction as that one goes from P1 to P2, that is in this one. So it's defined to be a localized vector. So these are your localized vectors. And it will be denoted by P1, P2 arrow, where P1 will be regarded as initial point and P2 will be regarded as the end point of the localized vector. Now, as the Euclidean geometry includes the length of a segment, and that will be considered here also. So the length of the segment is called the magnitude of this localized vector. That is, if you so this will be called the magnitude of the localized vector P1, P2 arrow, right? The magnitude. Fine. So now, why we have introduced this localized vectors? Because with this one we shall encounter one vector space. So, but what is the process of developing this vector space associated to this localized vector? So this is my aim. So let us denote X be the set of all localized vectors, right, in the space. Okay, fine. Now we define, so since we have a set, now our intention is to give you an equivalence relation on that set, but how it can be defined. So let us take two localized vectors. Suppose one is P1 arrow and another P1, P2 arrow, and another one is Q1, Q2 arrow. So if you have two localized vector, then you say that these two localized vector will represent the same arrow if they satisfy the following conditions. What are those? So the first one is, if you regard this arrow as a straight line segment, then this P1, P2 is parallel to Q1, Q2. This is the first condition. And the second one is that the straight line segment P1, P2 will have the same direction with Q1, Q2. So P1, P2 and Q1, Q2 will have the same direction. Okay. And the third one is that they have the same magnitudes. They have same magnitudes, right? Yeah, fine. Now this, if these two localized vectors will satisfy 1, 2, and 3, then we say that these two will represent the same arrow. And this is actually a relation, relation of being same arrow, right? Yeah, fine. So this is actually a relation of being same arrow on the set X. So you have a relation on the set X. Now we are always tempting to check whether it is equivalence relation or not. Now I will left this as an exercise, this theorem, that so if we denote, so the relation defined above will be an equivalence relation, right? Fine. So this is left as an exercise to you. So you can check, and it is very much obvious. Fine. Yeah. So let us denote this relation by this one, being same arrow. Yeah. So this is your notation. Okay. So once you have a equivalence, once you have an equivalence relation on a set, then you can construct a quotient set, right? So suppose you have an equivalence relation on X, then you can define a quotient set comprising of all the distinct equivalence classes determined by this relation. So here also we are considering the distinct equivalence classes of X under the equivalence relation, this. And we denote the set, so V denotes the set of all equivalence classes determined by this relation on the set X. So this is your quotient set with respect to this relation. Okay. And the members of this V will be called a vector. So members of this V are called vectors in the space. Now, one thing I should mention that I haven't defined the vector space. Okay. So I will tell you that just considering the axioms of Euclidean geometry, you can develop one example, and this is a classical one. The physicists are using this example actually. So arrows. Okay. So this example will give you the idea that yes, there is an associated vector space with respect to arrows. Then what is this? What is the associated vector space we are talking about? Okay. So, okay, fine. So the members of this V will be denoted in by the small letters like UVW, etc. Okay. Okay, fine. So if you consider a vector U in V and an arrow which is sitting in U, then this P1, P2 is called the localization of the vector. So this P1, P2 is called a localization of the vector U, right? Fine. Now, how could you define the zero vector? It is very easy because just take one point P, any one point in R3. Just take one point in R3, then you can define. So this is the zero vector, PP arrow, right? So actually this is a point. So you can define this like that. So this is the zero vector. The zero vector. Okay. Okay, fine. Then now if you consider one U, then by the equivalence relation, you can have that all the representatives will have the same magnitudes. So you can define actually the magnitude of a vector, and it is the magnitude of U is actually just take one representative from the vector and consider its magnitude. So this is denoted by this. Fine. And for this reason, note that the magnitude of the zero vector must be this, right? Now let us fix a point in R3. So let us fix a point O in R3. Okay, and regard this as the origin. Then you can actually represent any vector. You just take this as like that, but you can actually have the following one, that is, given any vector U, you can localize it to the vector with respect to the origin. Just take any one vector, just take this one, then you will have one. This is one. Suppose this. So this is the localization of this. So these two arrows are in the same equivalence class, U, right? So this is your U, and this is also in U. Okay, fine. So the reason is that this arrow is actually related to this arrow. Yes. Okay, fine. And similarly, if you consider any localized vector from the origin, then this will give you another class. That is, given any point P, then you can have this arrow, and then this will give you a vector in V. So a vector in V. Fine. Okay. Okay. So for that reason, we call these representation of vectors as position vectors. I think you might have seen this concept of position vectors, and it will be with respect to Cartesian coordinates. But I am not referring to this till now. Okay. Now note that. Okay. Okay. So this observation will tell us that for every vector u in V, you may consider the localization of this vector with respect to the origin. And this localization will give you one point, that is P, right? So this is, so actually for each P, you are getting one unique P. For each U, we are getting one unique point P in the space, R3, okay? So this P is sitting in the space R3. So you are having an association between the set of vectors with the points of R3. So that is, so this gives us a unique point. Suppose we can denote this by PU in R3. And so that one can associate a map, one can associate a map just give me 1 minute. Okay. Okay, fine. So that one can associate a map from U, map U to PU from the set capital V to R3, right? And this map has some special properties. Which are those? So the first thing is that this map is 1, 1. Why it is? Because just take 2 points P and Q. If they are same points, then they will give you the same vector, right? So this is very easy. I don't need to prove this. Very trivial. And the ontoness is also trivial. That is, given any point P in R3, so you can consider the vector OP, right? Okay, which will be determined by the point this. So in this way, you can say that this map is actually 1, 1 on 2. That is, this is, so you have set up a 1, 1 on 2 correspondence in between the set V of vectors onto the set of points in R3. So this is a bijection, right? Okay. Now, okay. So let me do something in hurry. Okay. So now, as you all know that, and I think you might have studied the how to take addition of 2 vectors, right? Actually, 2 localized vectors. So let us define an addition on V. Now, how to define this? Just take two vectors. So let U and V be two vectors in V. And suppose you have chosen two localization of one is for U and another one is for V, like that. Yeah. So this is, sorry, yes. And another one is like that, P2, P3. Yes. Right. Because if you consider any point outside the localized vector, you can always define a localization, right? So just if you have this, then if you consider this point, then you can have this one, right? So in this way, we are just taking this kind of thing. Okay. Then what will be the addition of these two vectors? Now, primarily, as we know that if you consider this one, so this is your P1, this is your P2, and this is your P3. So we need to define the addition of these two vectors in some sense that one has to reach P3 via just starts from P1, then go to P2, and then it will go to P3. And in some sense, this relative position of this P1 and P3, it will give you the position of this localization, that is P1, P3 arrow. So P1, P3 arrow will be the sum of the effects of these two localization, that is P1, P2 arrow and P2, P3 arrow, right? So we define U plus V as the class of localized vectors, whose one localization is P1, P2, this P1, P3 arrow, right? Fine. Okay. Now one may ask a question that whenever you are talking about some binary operation, then you need to say that it must be well defined, right? So otherwise we cannot work with that. So how can you show that this definition of addition is actually well defined? Why? Because if you consider another two localization of respective vectors U and V, suppose you have P1 dashed, P2 dashed arrow, it is in U, and P2 dashed, P3 dashed, this arrow is in V. So then, okay, so then you have that this will imply that this arrow is actually related to the previous one, since they are in the same class, right? And also for the case of V, this is actually related to P2, P3 class. So that is, if I can draw the pictures of localization, then you can, okay, just, yeah, right. So this is P1, this is P2, and this is P3. And this is your P1 dashed, this is your P2 dashed, This is your P3 dash. So then what will happen? Since these two localized vectors are related, these two localized vectors are related, so then you will have, I don't know, some noise is coming. Okay, thank you. Okay. So with respect to this relation, you can have, so these two localization will have same magnitudes, right? And for the case of this, yes. And also, you know that these two localizations, these are parallel to this one. So this is, yeah, yes, fine. So I need to, yeah, okay. Okay, fine. So then yes. Now this angle is also also you have that the angle P1, P2, P3 is equal to P1 dashed, P2 dashed, P3 dashed. Yes. Yes. Fine. Okay. Just using the fifth postulate of Euclid, you can easily, so this can be, okay, this is left as an exercise. Yes, fine. You can check that. These two angles are equal. And since these lines have same magnitudes, this one, and the angle is same. So what can we have? So by SAS, property of congruence between two triangles, this one and this one, so this one and this one, so you must have that these two triangles are actually congruent. So P1, P2, P3 is actually congruent to this triangle, right? Fine. And using this congruence, you can deduce that just P1, P3 of this magnitude is equal to P1 dashed, P3 dashed this, and certainly you will have P1, P3 is parallel to P1 dashed, P3 dashed, and they have the same direction. I don't need to specify this, right? Okay. So using this one, you can actually have for these two localization. So these two localization actually they are related to the relation that I have defined at the beginning, right? So these two vectors are same. Fine, great. So I have deduced that this is well defined. Fine. So just using geometry, you can define this addition, right? So this addition is actually from V cross V to V, and this is closed, right? And not only that, this can be treated as a theorem that for, suppose you have three vectors, then you can prove that this u plus v equal to v plus u, and this will satisfy associativity also. And surprisingly, you will have all the properties that you define to axiomatize a vector space. So that is, so I'm just doing the addition properties. So okay, fine. Yes, you will have this, and also for any vector u, you can define a unique additive inverse. So this equation has unique solution. Unique solution, and which can be denoted by this. Fine. So thus we have proved that actually with respect to this addition, the set V forms an abelian group. Fine. So this is the corollary, that V with respect to this addition forms an abelian group, right? So this is your first axiom of vector space, that you need to take one abelian group, right? Now we are moving to define the scaling, that is, for any vector, how can you zoom in and zoom out this vector, right? So just this, and then you can zoom out or you can zoom in. So how to define this? So let us consider a vector in V, and suppose you take one localization, PQ, okay? Now let alpha be a real, right? So then you define another localized vector which will be determined by these two objects, one from the field of reals and another from this abelian group. Now it is an abelian group, so we can talk about that. So okay, so P dash Q dash will be our new localized vector whose magnitude will be mod alpha times the magnitude of PQ. And what will be the direction? The direction of P dash Q dash arrow is same as PQ if alpha is greater than 0. The direction is same as that of PQ arrow. And if you take this negative, then it will have the opposite, right? So then the direction is opposite to PQ. Direction is opposite. Okay. Okay, fine. So you can easily check that this operation is from, so it denoted by dot, and this is from R cross V to V, denoted by, so I am just giving a notation of that. So this is your alpha comma B, and this will go to alpha V. So this is your new localized vector as we have defined above, right? And with respect to this definition, you can check easily that. So check on your own that the theorem is that for any three vectors u, v, w in V, and for any two scalars, I am just naming the members of R as scalars. Okay, fine. then one is like that, alpha b u is going to be alpha beta u going to be this or this one. Since R is commutative, so you can have this. And number 2 will be alpha u plus v is actually alpha u plus alpha v, right? And number 3 is alpha plus beta u is alpha u beta u. And number 4 will be, since R has unity, so unity will act like that. Just it will act as the identity, right? So 1 dot u goes to u. And this proves that, so this theorem will be left as an exercise before scarcity of time. So I'm not going to prove this. So the corollary will be like that, that this V forms, satisfies, so forms a vector space over R with respect to class and dot. So now you can feel that I have not yet defined the vector space, but I am defining this using the properties that we have obtained through this discussion on V. So what are those axioms? So now you can introduce the definition of vector space as like that, that you have, suppose, a definition of vector space. So suppose you have one set, suppose X be a set, and you need to consider one field. So I am assuming that you have already has a good knowledge of field, right? Okay. So let us consider a field F. Then you can say that X is said to form a vector space over F with respect to two operations. One is plus from X cross X to X, and another one, so this is regarded as, will be called vector addition. Then why it is called vector addition? Now it is clear to you, because classically it has been defined the way I have done, right? So now the another one is the scalar multiplication, right? Fine. Yes. So with respect to these two mapping, now plus will be like that. So suppose you have uv belongs to X, then it will go to the member u plus v, and for this scalar multiplication, so alpha comma u will go to alpha u. So then X is said to form a vector space if it satisfies the following. That is, the first one was that X plus forms an abelian group, right? Right. Now the second one. So I will not writing all this. So it is up to you. You will just complete this definition using the facts that I have obtained in V, right? So it is your task. Okay, fine. So the 1, 2, 3 that I have obtained in the space V of vectors with respect to addition and scalar multiplication. So that were the axioms to define an arbitrary vector space. Okay. And with respect to that, you will have an association between you have already an association between the points of R3 and the points, the vectors in the space V. Now this association is already a bisection, right? Okay, so okay, fine. How much time I have?
10 minutes.
Okay, fine. Okay, thank you. Okay. So yes. So okay. Right. So now, okay. So I'm going to prove that you can actually transport the operations from V to R3. But how? Now I am going to assume one theorem. I'm not going to prove this, but I want to assume. I'm just giving you the sketch of that proof because okay, fine. So what is the theorem? Any question? No. The noise are coming. So any questions? Okay, fine. So the theorem is like that one can find three vectors. One can find three vectors, and I can prove that E1, E2, E3 in V such that every vector V in capital V can be represented uniquely as like this one. Sorry, this is 2 and this is 3 for 3 unique scalars. This is in R. So how to get this? Just if you have, just consider, I'm just going to give you the sketch, and to state this theorem I need many things to prove, but due to the shortage of time I cannot do this. Okay, so I am going to just give you the sketch. So what is the sketch? Just okay, so this is your origin, and consider any two vectors which are non-collinear, right? So suppose this is E1 and this is your E2, right? Any two vector. Okay, then you can define another one vector. What is that? Suppose this is your E3, which is not sitting in the plane determined by E1 and E2, because we are in R3, so we assume the axiom of geometry that all planes are proper subspaces of R3, right? So since the plane determined by E1 and E2 and the origin, so this plane is a proper subset, and being a proper subset of R3, you can always have a vector outside that plane. Okay, and that, so this way you can consider any E3. Okay, Now what you do? So okay. So the localization I should mention. So this is your OP, this is your OQ, and this is your OR. Okay. Now you have one vector like that. Suppose it is A. Then what you will do? You will just consider the localization of this one, this. Okay, so this is your C, right? Suppose it is your V, your U, right? This is U. So this is your U. So I am just producing one line segment to meet this plane, and the line segment must be parallel to OR. Okay. So then you can have this. So then you will have this one. That is, what is your OA? So your OA is OC vector plus CA vector. Fine. Right? This is your OA. Now what is CA vector? Now what is OC vector? Now OC vector will be, so just if you produce this one, then you actually have this is suppose your B. So this is your OB plus BC, right? And plus CA vector. Fine. So thus, now what is OB? Now OB is parallel to OP vector, right? That is U1. So since they are parallel, then you can prove that, so they are actually a multiple of that vector. That is, you can have one alpha 1 through which you can express this vector. So it is alpha 1 U1. Okay. Now since BC vector is parallel to this one, so this is your, okay. So this vector is parallel to E2 vector. So you can actually have another scalar like this. And then you will have this one. Since this vector is parallel to this, right? So thus your U has been expressed as alpha 1 E1 plus alpha 2 E2 and alpha 3 E3. Now I would like to left the uniqueness part. So left as an exercise. The uniqueness part. That is the alpha 1, alpha 2, alpha 3. These are unique for the vector. And so using the map, so observation is like that. Observation is like that. So you have already defined a map from V to R3. And that map actually brings into this one, just using the coordinates. That is, if you have an U, then it will give you some PU, and this PU will have the coordinates alpha 1, alpha 2, alpha 3. And this map is a bijection, as we have already proved. And this bijection will transport the operations of addition and scalar multiplication from this set onto R3 using this map. That is, one can define addition alpha 1, alpha 2, alpha 3 plus beta 1, beta 2, beta 3, just coming back to this space and do the operation, and then you will have again the scalars, this one. Okay. And similarly for the scalar multiplication. So suppose you have an lambda. Suppose you have a lambda and you have one point like this. So this can be defined like the way we have defined addition to this. So R3 is equipped with these two operations. And since V has already satisfied all the axioms of a vector space, similarly, R3 with respect to these operations will satisfy all those vector space axioms, right? So you have this corollary that R3 with respect to this addition and scalar multiplication is actually a vector space over R. Not only that, this map preserves the operations. That means what you have done using geometry is actually linearly isomorphic to R3 plus dot. And that is why this is your associated vector space when you are experimenting with arrows. So this is your vector space associated to this Euclidean geometry, right? So thank you.
Okay, sir. Thank you very much for such interesting presentation. You have given a different introduction to vector spaces. As many of the participants have said that, I also think so. Very nice presentation. I am sure that all the participants have been benefited from your lecture. Now I have gathered 2 or 3 questions from the chat box.
Okay.
Pratap Shan raised that why we need linear algebra for studying.
Why? Okay. So okay. There are several classical things that you have to define vector space axiomatically, because you need to increase your dimension, right? So you need to go from R3 and R2 to R4, R5, and so else like that. And another one is to just using. So if you are just discussing the problems in differential equations, you will find that the problem of, suppose you have a non-homogeneous differential equation, ordinary differential equation, then the solution space of the associated homogeneous system will generate the complete solution space, just using one translation by a particular solution. Right? So you have many applications of linear algebra.
Okay. Nitesh Shenoy raised that what is the application of linear algebra?
There are several applications. Whenever you are talking about addition, scalar multiplication, you need to have linear algebra and more. And if you want to go advanced, then you need to have module theory, right? So which will give you the general version of vector space, where you need to consider rings, right? Instead of taking fields.
Anupam Sharma said that which topics of linear algebra are active in the field of research?
Okay. There are many things. So I think you just Google, and you can search everywhere that linear algebra is there. Whenever you are talking about addition and scalar multiplication, so if you are concerned, then you will have.
Thank you, sir.
Thank you.
We are really very much grateful to you.
Thank you.